So yesterday I ended up not doing anything more than I did when I stopped. So I'm gonna continue from where I left off. And I think I'm gonna take my time on this one because Web3 seems to be important. I think it's an API that connects the blockchain with the outside world. So by completing lesson 5, our zombie app is now complete. Now we're going to create a basic web page where your users can interact with. To do this, we're going to use a JavaScript library from the Ethereum Foundation called Web3.js. Remember, the Ethereum network is made up of nodes, with each containing a copy of the blockchain. When you want to call a function on a smart contract, you need to query one of these nodes and tell it the address of the smart contract, the function you want to call, and the variables you want to pass to that function. Ethereum nodes only speak a language called JSON RPC, which isn't very human readable. A query should tell the node you want to call a function on contract looks something like this. Look, writing all your function calls this way. So it's pretty much an API, similar to an API call. Luckily, Web3 hides these nasty queries below the surface, so you only need to interact with a convenient and easily readable JavaScript interface. Instead of needing to construct the above query, oh wait a minute, I forgot to close Discord. So let me close that. Okay. Instead of needing to construct the above query, calling a function in your code will look something like this. Okay. We'll explain the syntax in detail over the next few chapters, but first let's get your project set up with web3.js. Getting started, depending on your project's workflow, you can add web3.js to your project using most package tools. Yeah, but I don't think I'm not gonna need to do this here. Or install, or you can simply download the minifield.js file from GitHub and include it in your project. So this is probably the one that I'm using. Script language, JavaScript, type, text, JavaScript. I was thinking about it. I wonder if there's a way to have a blockchain that you don't necessarily need to update everyone's nodes for everything you have to do, because that would allow the blockchain to be a lot faster and less expensive. There must be a middle way between a blockchain and a standard regular database, I think. Because yeah, I think the normal databases are faster because they're centralized, so the resources are not all in the same place, so it's more dynamic to access, I think. And on the blockchain, everything is stored kind of in the same place because everyone has the same nodes, has the same blocks. So it ends up creating something that over time becomes too inefficient, I think. But I'm not sure. They probably calculated how long it will take until it becomes unfeasible to do anything, because it's so slow that there's so many blocks that you can't do anything. And it's probably a very long time, but I wonder if there is a way to mix both. I think there is. I think there probably is, because if there is a polarization, there needs to be something in the middle to connect. So I think it might be something that is worth thinking about and interesting to think about, because that's probably where things will go eventually. Because that's how everything works. It goes from one side to the other and constantly creating new stuff. Since we don't want to make too many assumptions about your development environment and what package manager you use for this tutorial, we're going to simply include Web3 in our project using a script tag as above. Put it to the task. So I think it's just like what I did. Yeah. Now that we have Web3 in our project, let's get initialized and talking to the blockchain. The first thing we need is a Web3 provider. Remember, Ethereum is made up of nodes that all share a copy of the same data. Setting a Web3 provider in Web3.js tells our code which node we should be talking to handle our reads and writes. It's kind of like setting the URL of the remote web server for your API calls in a traditional web app. You could host your own Ethereum node as a provider. However, there is a third-party service that makes your life easier, so you don't need to maintain your own Ethereum node in order to provide the depth for your users. Infura is a service that maintains a set of Ethereum nodes with a caching layer for fast reads, which you can access for free through their API. Using Infura as a provider, you can reliably send and receive messages through from the Ethereum blockchain without needing to set up and maintain your own node. You can set up Web3 to use Infura as your Web3 provider as follows. It might be interesting as well to read stuff about how the Ethereum virtual machine works. I think that's might be quite interesting as well, because it's probably the way that I imagine it works right now is a set of rules and heuristics that provide the network environment. So they dictate what you can do and what you can't. So I think it's probably very important to know. The thing is that there are so many other protocols, and I'm not even sure if Ethereum is gonna be the biggest one. Probably not, to be honest. I think usually the first one is not the biggest one, so I think there will be other ones. I'm not sure if it's gonna be Cardano or not, but yeah, maybe they are all based on Ethereum in some way, so it might be worth it to study Ethereum. It's just a question of how much time I'm gonna spend reading the repo. You can set up Web3 to use Infura as a Web3 provider as follows. So var, actually I'm gonna write it down just to memorize it better. WebSocket provider. However, since our dApp is going to be used by many users, and these users are going to write to the blockchain, not just read from it, we will need a way for these users to sign transactions with their private key. Note Ethereum and blockchains in general use a public private key prior to digitally. Cryptography is complicated, so unless you're a security expert and you really know what you're doing, it's probably not a good idea to try to manage your users' private keys yourself in our app's front end. Luckily, you don't need to. There are already services that handle this for you. Most popular of these is MetaMask. MetaMask is a browser extension for Chrome and Firefox that lets users securely manage their Ethereum accounts and private keys. Use these accounts to interact with websites that are using Web3.js. If you haven't used it before, you'll definitely want to go and install it. Then your browser is Web3 enabled, and you can now interact with any website that communicates with the Ethereum blockchain. And as a developer, you want users to interact with your dApp through a website in their web browser, like we're doing with our CryptoZombies game. you definitely want to make it MetaMask compatible. What MetaMask uses servers under the hood as a Web3 provider, just like we did above, but it also gives the user the option to choose their own Web3 provider. So by using MetaMask Web3 provider, you're giving the user a choice, and it's one last thing you have to worry about it in your app. Using MetaMask Web3 provider. MetaMask injects their Web3 provider into the browser in the global JavaScript object Web3, so your app can check to see if Web3 exists, and if it does, use web3.current provider as its provider. Here's some template code provided by MetaMask for how we can detect to see if the user has MetaMask installed. Do not tell them they will need to install it to use your app. Just some event listener. So if it's undefined, creates a new object of the provider. And in the case where it's not Web3 probably show, so probably console error, an error message. You can use this boilerplate code in all the apps you create in order to require users to have MetaMask to use their app. Note, there are other private key management programs your users might be using besides MetaMask, such as the web browser Mist. However, they all implement a common pattern of injecting the variable Web3, so the method we describe here for detecting the user's Web3 provider will work for this as well. Put it to the task. Go ahead and copy and paste the template code above for detecting MetaMask. It's the block that starts with. So, well, now I'm not sure if I should raise this. Probably should raise. I think I'm gonna write it down just to exercise my memory. So great, doesn't show me that. I think maybe I need to have the other one as well. Yeah, because if I don't, then I'm gonna create the object. It's probably the mistake. Or maybe not. So what's it? Add event listener load function. Type of Web3 define Web3 chance for view. Web3 pipeline. Maybe I should paste this one inside of it. Copy and paste the template code from above for detecting MetaMask. Oh, I forgot to start app. That's the problem. Chapter 3, talking to contracts. Now that we've initialized Web3.js with MetaMask Web3 provider, let's set up to talk to our smart contract. Web3 will need two things to talk to our contract, its address and its API. After you finish writing your smart contract, you compile it and deploy it to Ethereum. We're going to cover deployment in the next lesson. But since that's quite a different process from writing code, we've decided to go out of order and cover Web3 first. After you deploy your contract, it gets a fixed address on Ethereum where it will live forever. If you recall from lesson 2, the address of the CryptoKitties contract on Ethereum mainnet is this one. You need to copy this address and after deploying in order to talk to your smart contract. Contract API. The other thing Web3.js will need to talk to your contract is its API. ABI stands for Application Binary Interface. Basically, it's a representation of your contract's methods in JSON format that tells Web3 how to format function calls in a way your contract will understand. When you compile your contract to deploy to Ethereum, which we'll cover in lesson 7, the Solidity compiler will give you the API. So you need to copy and save this in addition to the contract address. Since we haven't covered deployment yet, for this lesson we've compiled the API for you and put it in a file named CryptoZombies API.js, stored in a variable called CryptoZombies API. If we include CryptoZombies API in our project, we'll be able to access the CryptoZombies API using that variable. Instantiating a Web3.js contract. Once you have your contract's address and API, you can instantiate it in Web3 as follows. So just create the object web3js.ethereum.contract. Then my API and my contract address. In the head of our document include another script tag for CryptoZombies, Zombies API.js, so you can import the script. I'm not sure, I probably need to do this language called JavaScript. Seems a little bit redundant to do that every time, instead of just doing the type text JavaScript. CryptoZombies API.js. At the beginning of our script tag, so here, declare a var named CryptoZombies, but don't set it equal to anything. Here we use this variable to store our instantiated contract. Let's create a function named so I assume it's right after this. Function name startup. Should do in the body next just time. The first thing startup should do is declare a var named CryptoZombies address and set it equal to the string or contract address. This is the address of the CryptoZombies contract on mainnet. Lastly, let's instantiate our contracts. Set CryptoZombies equal to a new Web3.js Ethereum contract, like we did in the example above. So I assume it's here. Set CryptoZombies. I think it's new. Yeah. Web3.js Ethereum contract. Using CryptoZombies API, which gets imported with our script tag and CryptoZombies address from above. So it's CryptoZombies API, crypto address. And so it needs to have opening and close brackets. This is probably the path, is incorrect. or the way that I wrote it actually. Or maybe not. Oh yeah. So it might be the yeah, I don't understand. Because it should be on the same directory, so oh, it's probably the comment. But now I'm wondering if the other things were wrong, like the opening and closing tag, or if you can do that, or whatever. Calling contract functions. Our contract is all set up. Now we can use Web3.js to talk to it. Web3 has two methods we will use to call functions on our contract, call and send. Call is used for view and pure functions. It only runs on the local node and won't create a transaction on the blockchain. Review. View and pure functions are read-only and don't change state on the blockchain. They also don't cost any gas, and the user won't be prompted to sign a transaction with MetaMask. Using Web3.js, you would call a function named myMethod with the parameter 123 as follows. So it doesn't create transactions. I read only, don't change the state. Okay. So it doesn't create transactions, but it reads from the blockchain. Send will create a transaction and change data on the blockchain. You need to use send for any functions that aren't view or pure. Note sending a transaction will require the user to pay gas and will pop up their MetaMask to prompt them to sign a transaction. When we use MetaMask as our Web3 provider, this all happens automatically when you call send, and don't need to do anything special in our code. Pretty cool. Using Web3.js, you would send the transaction calling a function named myMethod with parameter 123 as follows. The syntax is almost identical to call. Getting zombie data. Now let's look at a real example of using call to access data on our contract. Recall that we made our array of zombies public. In Solidity, when you declare a variable public, it automatically creates a public getter function with the same name. So if you wanted to look up the zombie with the ID 15, you would call it as if it were a function. Here's how we would write a JavaScript function in our front end that would take a zombie ID, query our contract for that zombie, and return the result. All the code examples we are using in this lesson are using version 1 of Web3.js, which uses promises instead of callbacks. Many other tutorials you see online are using an older version of Web3. Syntax changed a lot with version 1. So if you're copying code from other tutorials, make sure they're using the same version as you. So it just uses the call method here and then calls the function with the ID, and then does something with the promise. The resolution, the resolve of the promise by stringifying what came back. Communicate. I think I need to read that. So it will be JavaScript object with the struct of the zombie. We could then have some front-end logic to parse the object and display it in a meaningful way on the front-end. Put it to the task. We've gone ahead and copied getZombie details into the code for you. So this method's call. If you recall from Zombie Factory, saw we had a mapping that looked like zombie owner. Define a JavaScript function called zombie show owner. So it's a function. Define a JavaScript function called zombie show owner. Similar to get zombie details above, it will take an ID as a parameter. Zombie, probably that's what they want me to do. Methods dot zombies id dot call. And we return a web3 JS call to zombie owner on our contract. Below that create a third function for get zombies by owner. If you recall from zombie hyper, the function definition looked like this. Our function get zombies by owner will take owner as a parameter and return web3.js call should get zombies by owner. So function get zombies by owner takes an owner. So I guess it's pretty much the same thing. And zombies as the other two methods. Zombies might be different actually because of this zombies ID that I don't understand really well what it is. Yeah, this is different probably. Probably owner, but I don't understand this call really well. I guess it's calling the function on the contract, then the methods of the whatever you're calling. Maybe here is zombie owner and stuff. Yeah, don't know. So it has to be CryptoZombies because I'm accessing CryptoZombies, which is this thing here. Then it's calling the methods on this, and then is the other thing. So here's probably zombies show owner, and here's probably get zombies. Yeah, now that makes more sense. Not sure if it's correct, but makes a lot more sense than to me than what I was doing before. Let's see. Also, I need to erase this. Oh, in here, I forgot this. Yeah, there we go. So first, it calls you use the provider object, then you access the methods, then you access whatever function you're trying to get. Awesome, you've successfully written front-end code to interact with your first smart contract. Now let's put some pieces together. Let's say we want our app's homepage to display a user's entire zombie army. Obviously, we'd first need to use our function getZombies by owner to look up all the IDs of zombies the current user owns. But our Solidity contract is expecting owner to be a Solidity address. How can we know the address of the user using our app? Getting the user's account in MetaMask. MetaMask allows the user to manage multiple accounts in their extension. We can see which account is currently active on the injected Web3 variable via web3.ethereum.accounts. Because the user can switch the active account at any time in MetaMask, our app needs to monitor this variable to see if it has changed and update the UI accordingly. For example, if the user's homepage displays their zombie army, when they change their account in MetaMask, we want to update the page to show the zombie army for the new account they've selected. We can do that with a set interval loop as follows. So it's pretty much checking after 100 milliseconds, I guess. Call if account has changed, so user account. Call the same function to update the UI with the new account. Yeah, I'm not sure if they talk about what is this function here. But I guess it's just changing the variable with the account. What this does is check every 100 milliseconds to see if user account is still equal this account. Does the user still have that account active? If not, it reassigns user account to the currently active account and calls a function to update the display. Declare a var named user account. User accounts. At the end of startup, so here, copy and paste the boiler template account interval code from above. I think I'm just gonna write it down to train my memory. User accounts equals Web3. Update interface. Replace the line update interface with a call to getZombies by owner and pass it user account. So it's here, user account. Oh, so this is the thing that is gonna get the account. Get the zombies on the account. Chain a chain statement after getZombies. and pass the result to a function named display zombies. We don't have a function called display zombies yet, but we'll implement it in the next chapter. Displaying our zombie army. This tutorial wouldn't be complete if we didn't show you how to actually display the data you get back from the contract. However, realistically, you want to choose a front-end framework like React or Vue.js in your app, since they make our life a lot easier as a front-end developer, but covering React or Vue.js is way outside the scope of this tutorial. That would be an entire tutorial of multiple lessons itself. So in large, keep CryptoZombies.io focused on Ethereum and smart contracts. We're just going to show a quick example in jQuery to demonstrate how you could parse and display the data you get back from your smart contract. It's pretty much just using the data and stringifying, transforming from JSON to JavaScript. And then you can destructure the object, I think, to get the information that you want. In React, you can use props to pass the data down the tree. Displaying zombie data. A rough example. We've added an empty zombie div to the body of our document, as well as an empty display zombies function. Recall that in the previous chapter we called display zombies from inside start app with the result of a call to get zombies by owner. It will be passed an array of zombies IDs that looks something like. Thus we will want our display zombies function to first clear the contents of the zombies div if there's anything already inside it. This way, if the user changes their active MetaMask account, it will clear their old zombie army before loading the new one. Yeah, probably you would use state in React actually, with a map or something like that, to display the stuff. Loop through each ID and for each one call get zombie details ID to look up all information for the zombie from our smart contract. Then put the information about the zombie into an HTML template to format it for display, and append that the template to the zombies div. So I have the app here, count interval. And I probably will need to write this stuff they're talking about. So the div is here. Again, we're just using jQuery here, which doesn't have a templating engine by default. So this is going to be ugly, but here's a simple example of how we could output this data for each zombie. So get zombies, zombie details ID, then function using esse template literals to inject variables into the HTML. So zombies dot append. It's getting this div and appending a new div with class zombie, and then parsing the data like this. What about displaying the zombie sprites? In the above example, we're simply displaying the DNA as a string, but in your dApp, you would want to convert these two images to display your zombie. We did this by splitting up the DNA string into substrings, and having every 2 digits correspond to an image, something like. I wonder how images are stored. How NFTs are stored in the blockchain. It's probably through strings, about your guess, maybe a string that has a that gets triggered by a hash function or something like that to convert it to an image. Get an integer 1 to 7 that represents our zombie ad. Yeah, so here is a string with a unique identifier. But I'm not sure if this is in the blockchain or it would be in the front end. Probably in the front end because of the structure. Each component is positioned with CSS using absolute position to overlay it over the other images. If you want to use it to see our exact implementation, we've open sourced the Vue.js component we use for the zombies appearance, which you can view here. However, because there's a lot of code in that file, it's outside the scope of this tutorial. For this lesson, we're stuck with the extremely simple jQuery implementation. I leave it to you to dive into a more beautiful implementation and so on. Interesting. Yeah, so this stuff probably sits on in the front end. But then still brings me the question of how NFTs are stored. Or maybe, yeah, this has to be on the front end, I think. Created an empty display zombies function as filtering. The first thing we want to do is empty the zombies div. In jQuery you can do this with zombies. I don't know jQuery actually. Some people say that it's not used as much nowadays, so I think it might not be worth it to study, because I can spend my time studying other things. Next we want to look through all the IDs using a for loop. Inside the for loop, copy paste the code block above that called get zombies ID, details ID for each ID, and then used zombies.append to add it to our HTML. Yeah, I already forgot the way that is written there, so I'm gonna have to look. So backticks. Oh, actually, this is here. And then the UL stuff I'm gonna copy. And here is div. think this is correct. Chapter 7, Sending Transactions. Put new music. Also now our UI will detect the user's MetaMask account and will automatically display their zombie army on the homepage. Now let's look at using send functions to change data on our smart contract. There are a few major differences from call functions. Sending a transaction requires a from address of who Sending a transaction requires a from address of who is calling the function, which becomes message.sender in our Solidity code. We want this to be the user of our app, so MetaMask will pop up to prompt them to sign the transaction. Sending a transaction costs gas. There will be a significant delay from... I think I'm gonna change this music, sure. It's too much. There will be a significant delay from when the user sends a transaction and when that transaction actually takes effect on the blockchain. This is because we have to wait for the transaction to be included in a block. The block time for Ethereum is on average 15 seconds. If there are a lot of pending transactions on Ethereum, or if the user sends too low of a gas price, our transaction may have to wait several blocks to get included. This could take minutes. Thus we need logic in our app to handle the asynchronous nature of this call. Creating zombies. Let's look at an example with the first function in our contract. A new user will call create random zombie. As a review, here's the Solidity code in our contract. Here's an example of how we could call this function in Web3 using MetaMask. So guess the div of this ID. Create a new zombie. So it's just displaying the message. Send the transaction through our contract. .send. So it's first getting the create zombie, then send from account. On receipt function successfully created. Transaction was accepted in the blockchain. Let's redraw the UI. Something to alert there. I guess it's not necessary to write async here anymore. Because this zone probably does that. Our function sends a transaction to our Web3 provider and chains some event listeners. Receipt will fire when the transaction is included into a block on Ethereum, which means our zombie has been created and saved on our contract. Error will fire if there's an issue that prevented the transaction from being included in a block, such as the user not sending enough gas. We want to inform the user in our UI that the transaction didn't go through so they can try again. Note you can optionally specify gas and gas price when you call send, e.g. send. If you don't specify this, MetaMask will let the user choose these values. Put it to the test. we've added a div with ID transaction status. We can use the div to update the message. Below display zombies, copy and paste the code from create random zombie above. So below the display zombies. Zombie on the block. Okay. It's made. Just returns the zombies thing. Let's create random zombie. Name. Sounds. User. Mouse. On function 6. Let's implement another function, feed on kitty. The logic for calling feed on kitty will be almost identical. We send a transaction that calls the function, and a successful transaction results in a new zombie being created for us. So we want to redraw the UI after it's successful. Call the second function feed on kitty, which takes 2 arguments, zombie ID and kitty ID. Make a copy of create zombie right below it, but make the following changes. So I guess I need to copy this one. Feed on kitty. Or maybe I don't need to change the name, it's just the stuff inside here. Let anti-eating kitty. Make it call video on kitty on our contract. So here's feed on kitty, and then public kitty ID. And pass the same 2 arguments. So it's probably here. The success message on text should read ate a kitty, spawn a new zombie. So now I'm not sure, it's probably 8 then kitty ID. And then this here. Zombie ID plus did I forget to change the name? Maybe I should have erased this. Yeah, I'm not sure. Yeah, it's analyzing like is this one. Or no, now it's analyzing this one. So the message is probably wrong. And the name as well. So I'm just gonna copy this one. Oh. Apparently here is wrong as well. Yeah, I think I'm gonna have to look at the solution. I don't really understand what I have to do here. To below, copy and paste this. Sufiram aqui. So maybe I just wrote something wrong or successfully here. That's the problem, I think. Yeah, there we go. Because I didn't copy, I just wrote it. The logic for attack, change name, and change DNA will be extremely similar, so they're trivial to implement, and we won't spend time coding them in this lesson. In fact, there's already a lot of repetitive logic in each of these function calls, so it would probably make sense to refactor and put the common code in its own function, and use a templating system for the text status message. Already we're seeing how much cleaner things would be with a framework like Vue.js. Calling payable functions. Let's look at another type of function that requires special treatment in Web3.js, payable functions. Call is OB help here. The way to send ether along with a function is simple. With one caveat, we need to specify how much to send in away, not ether. This way, away is the Smallest subunit of ether, there are 10 to the power of 18 way in 1 ether. I don't understand who made these measurements. Why make it so big? There must be a reason for that. I just don't get it. Maybe they were thinking about inflation if it goes on for a long time, but yeah, might be that, but I'm not sure. Because it's so annoying to use these very small or big numbers to make transactions and convert to dollars. That's a lot of zeros to account, but luckily Web3.js has a conversion utility that does this for us. This will convert 1 Ethereum to way. In our dApp we set level up fee 0.01 Ether, so when we call our level up function we can make the user send 0.001 Ether along with it using the following code. So you access the methods, the level up, and passes the zombie ID. Then it sends from this account this value. Put it to the test. Let's level up function below here. Okay. So function zombie ID. Zombie ID. This code should be very similar to feed on Kitty. The transaction should display the text status text leveling up your zombie. Then return should send 0.0 Ethereum converted to way as in the example above. I first need to call the methods. And I forgot which one is it. This is probably just level up and then the ID. Dot then. Actually dot send. From user account value Web3.js utils dot true way 0.001. It's there. And then on sift action status dot text. And here I think is the same thing. Probably. Just going to display the zombies. Then on arrow. status. Don't need to redraw the UI by querying our smart contract with get zombies by so. Because in this case we know the only thing that's changed is the one zombies level. As you can see, I think I'm gonna go to the bathroom real quick. As you can see, interacting with your... change the music, I think. I'll put this on again. As you can see, interacting with your contract via Web3 is pretty straightforward. Once you have your environment set up, calling functions and sending transactions is not all that different from a normal web API. There's one more aspect we want to cover, subscribing to events from your contract. Listening for new zombies. If you recall from Zombie Factory, we had an event called New Zombie that we fired every time a new zombie was created. In Web3, you can subscribe to an event, so your Web3 provider triggers some logic in your code every time it fires. CryptoZombies.events.newZombie. On data, that zombie equals event return value. Note that this would trigger an alert every time any zombie was created in our dApp, not just for the current user. What if we only wanted alerts for the current user? Using indexed. In order to filter events and only listen for changes related to the current user, our Solidity contract would have to use the indexed keyword, like we did in the transfer event of our ERC 721 implementation. In this case, because from and to are indexed, that means we can filter for them in our event listener in our front end. Current user just received a zombie. As you can see, using events and indexed fields can be quite a useful practice for listening to changes to your contract and reflecting them in your app's front end. Querying past events. We can even query past events using get past events, and use the filter from block and should to give Solidity a time range for the events logs. Block in this case referring to the Ethereum block number. Because you can use this method to query the event logs since the beginning of time, this presents an interesting use case, using events as a cheaper form of storage. If you recall, saving data to the blockchain is one of the most expensive operations in Solidity, but using events is much cheaper in terms of gas. Trade-off here is that events are not readable from inside the smart contract itself, but it's an important use case to keep in mind if you have some data you want to be historically recorded on the blockchain so you can read it from your app's front end. For example, you could use this as a historical record of zombie battles. You could create an event for every time one zombie attacks another one. The smart contract doesn't need this data to calculate any future outcomes, but it's useful data for users to be able to browse from the app's front end. Let's add some code to listen to transfer events and update our app's UI if the current user receives a new zombie. We'll need to add this code at the end of the startup function to make sure the CryptoZombie contracts has been initialized before adding an event listener. At the end, so here, startup here. Yeah, so first you need the object of the contract. And update here. At the end of startup, copy paste the code block above for CryptoZombies events.transfer. I think I'm gonna copy like this. I'm gonna write it down. Events.transfer. For the line to update the UI, is get zombies by number user account then display zombies. So I guess it's here. I guess I have to copy paste this stuff inside of here. Not really sure. Because this is an event, so maybe. Oh, it works. I don't understand really well though. Because you're just getting information from the event. So how can you, why do you need to display the zombie? Update, why do you have to update the UI? Or it's probably just to show the zombie that was transferred. Next steps, implementing functions. I'm not gonna read all of this. We now have all the skills you need to code a smart contract in the front end that allows to interact with. You're going to deploy your smart contract, yeah. So this one should be the most interesting so far to me. I'm not sure why it's not showing the next lessons here. The other one did the same thing. I'm just gonna go through here. Maybe here. Okay, so this might be a good time to stop and take a break, because I just finished the first section. Then I can continue on the other ones. And it's probably gonna take me a long time to finish, especially assuming that this part is gonna be harder than this one. So I think I'm gonna do this one now, and then I stop after this one. It's probably better. Just keep getting more impressive by the second, blah blah blah. Okay, start. Now let's suppose you're building a DeFi app and want to give your users the ability to withdraw Ethereum worth a certain amount of USD. To build this request, your smart contract, for simplicity's sake, we'll call it this color contract from your own nodes, must know how much 1 Ether is worth. And here's the thing, a JavaScript application can easily fetch this kind of information, making requests to the Binance public API or any other service that publicly provides a price feed. But a smart contract can't directly access data from the outside world. Now we could build a JavaScript application ourselves, but then we are introducing a centralized point of failure. We also couldn't just pull from the Binance API because that would be a centralized point of failure. So what we want to do is get our data from both a decentralized Oracle network and decentralized data sources. Chainlink is a framework for decentralized Oracle networks, and is a way to get data in from multiple sources across multiple oracles. This DOM aggregates, so decentralized Oracle networks, aggregates data in a decentralized manner and places it on the blockchain in a smart contract, often referred to as a price reference feed or data feed, for us to read from. So all we have to do is read from a contract that the Chainlink network is constantly updating for us. Using Chainlink data feeds is a way to cheaply, more accurately, and with more security gather from the real world in this decentralized context. Since the data is coming from multiple sources, multiple people can partake in the ecosystem, and it becomes even cheaper than running even a centralized oracle. The Chainlink network uses a system called off-chain reporting to reach a consensus on data off-chain and report the data in a cryptographically proven single transaction back on-chain for users to digest. You can then make protocols like Syntax, AAV, and Compound with this. Yeah, this is very interesting to me. Off-chain reporting is the next Oracle network upgrade replacing the Flux aggregator model. It represents a significant step towards increasing the decentralization and scalability of Chainlink networks. See the OCR protocol paper for a technical deep dive. Change summary. In the Flux aggregator model, every node must submit their price value individually. Once all responses are received on-chain, the contract aggregates them to confirm the price. The solution has been highly effective and reliable since its release. However, there are some drawbacks. Since every single node must submit a transaction per round, each pays gas to do so, with aggregation occurring on-chain once all nodes have submitted. The For off-chain, partner aggregators, all nodes communicate using a peer-to-peer network. During the communication process, a lightweight consensus algorithm is run, in which every single node reports its price observation and signs it. A single aggregate transaction is then transmitted, saving a significant amount of gas. The report contained in the aggregate transaction is signed by a quorum of oracles and contains all oracles' observations. By validating the report on-chain and checking the quorum's signature on-chain, we preserve the trustlessness properties that many have come to expect from Chainlink Oracle networks. Simple analogy: imagine ordering 10 items from an online store. Each item is packaged separately and posted separately, meaning postage and packaging costs must be applied to each one. The carrier should transport 10 different boxes. This is how Flux Aggregator works. Osteria, on the other hand, packages all of these items into a single box and posts that. This saves postage and packaging fees and all efforts the carrier associates with transporting 9 fewer boxes. So that makes me question how is the size of the boxes decided? Is it based on block size? I think I'm gonna dive deeper into this after I finish the course. After I finish all the CryptoZombie lessons. I hate when the browser does that or it immediately translates to my language. It's so annoying. I don't want them deciding for me what language do I wanna read this stuff. Syntax is a new financial primitive enabling the creation of synthetic assets, offering unique derivatives and exposure to real-world assets on the blockchain. Centralized perpetual futures. Leveraging the syntax depth pool and our innovative liquidity framework, our traders are guaranteed to have some of the best price execution on little to no slippage and feels you can't get anywhere. Also, capture the price movements of popular cryptocurrencies, fiat currencies, stocks, commodities, and more with zero slippage. Synthetic assets are assets voted into existence by the community and can come in the form of fiat currencies, cryptocurrencies, stocks, commodities, and anything else with a price. Platforms already leverage the deep liquidity and composability of syntax to deliver better trades with lower slippage, hedging, and other unique use cases. Another interesting thing is the governance. How are the governance for these things decided? I think eventually we're gonna have to move on to something that takes the power away from people and puts on systems that are based on first principles in the laws of physics, so that the structure of society doesn't collapse with exponential attack. But it doesn't have to, it can't be binded by supply and demand, I think, because then we fall into the problem of the limbic system overfeeding the environment. Because the incentive is always going to be based on what the consumer wants, which is the demand. And the consumer is the limbic system, and the limbic system lacks nuance and understanding of the implications. And because the regulation is based on the same incentives, it's going to be corrupted through time. So I think that this is why it's interesting to me, these governance things and how are people creating them, because I think we need to figure out a way to make the system not based on supply and demand, but based on the laws of physics. So pretty much code the structure of incentives around a different logic, let's say, rather than supply and demand. But the question is how you do that. That's the challenge. And I don't think that the blockchain is necessarily, I think the technology might be the way, but it's not necessarily the way that is being done now. It's not fully decentralized as far as I understand, because you have miners and there's also disconnections between centralized companies and the blockchain in order to make everything work. So even if it's proof of stake instead of proof of work, where people invest their money in order to dictate the validity of the transactions, is still not decentralized. It's just pretty much the same infrastructure, but changing who has more power inside of the infrastructure, from governments to who has money, because who has money decides the laws based on the governance and the algorithms, for as far as it seems, for the most part. I think if we could change that into something that's based on the laws of physics instead of the way that social structures evolve over time. But then is the question of, is it even possible to come up with an algorithm or a network of algorithms that can update itself so it's anti-fragile in relationship to the future? Because that's the biggest problem. You can't put the universe in an equation because it's computationally reducible. So how do you find the best distribution of these abstractions into programs in order to get something like this, where the incentives of innovation are aligned with the best overall distribution of power inside of the structure? Bond is an algorithmic autonomous interest rate protocol built for developers to unlock a universal open financial applications. Secure protocol for money. There's also this problem with Ethereum that everything has to be stored in the same chain, because there needs to be, because the nature of the thing. So the more it grows, the more inefficient it becomes in a way, because you're having to repeat the same thing over and over again instead of dynamically allocating the stuff that you need. So everyone has to have the same things instead of allowing for specialization in different areas, which is, I think, a big problem, because I think life evolves around the environment and social structure as well. That's why you have different languages and different ethnicities and the way that people speak. The social structure adapts to the environment through the lens of a market economy over time, or democracy, or different politics, or the systems, which is a self-reinforcing feedback loop, because it evolves based on the stimulus of the environment. Then the stimulus creates the systems based on the flow of information that creates the abstractions, and then those abstractions change the system again, which then changes the stimulus and goes like this. And that's why it overfits the environment, because it's asymmetrical in expansion, because the intuitive is linear and the abstraction is exponential. So the thing is, you have to strike the best balance between decentralization and decentralization on the distribution of power, so that you can allow for innovation and everyone is not trapped by whoever has access to the most data and can manipulate the data to control everyone else, but at the same time not be like the way that things are today, where everyone has access to the same nodes, and it doesn't allow for flexibility and specialization, because over time it's probably gonna break at some point, I think. At least if this logic makes sense. But then, if you think about a way to connect the both, is really, really hard. Like, what's the bridge between having these decentralized nodes where everyone has the same information, to a more dynamic one where it's still decentralized, but it's also centralized in a way where you have specialties. And maybe that's what's happening already with different protocols and different networks. And then there will be, maybe there already is, a lot of protocols that connect the other ones. And those protocols will be like the countries we have today, which will probably follow geometrical structure as well, because that's probably how social structures evolve through time. That's why I have countries. It's the abstraction of the flow of information between people. But yeah, but then it defeats the purpose of the decentralization anyway, because you're just gonna get the same thing but in a different way. So I think the only way is probably automation, but then it becomes a question of the design of the algorithms, which is also very difficult because of the paperclip problem. Now let's suppose you're building a DeFi app and want to give your users the ability to withdraw ETH worth a certain amount of USD. To fill this request, your smart contract, for simplicity's sake, you call it the color contract. From here onwards, must know how much one Ether is worth. And here's the thing, a JavaScript application can easily fetch this kind of information, make requests out. I think I already read this. Yeah. So I stopped here, I think. You can see visualizations of some of these DOMs here. So I guess these are all companies that use Oracle, that use Chainlink. There's a lot of them. Yeah, anyone can create one, so. You can see, we'll go into exactly how these networks tick in later lessons. So let's learn how to read from one of these data feeds. The first thing we want to do is start our contract and import the chainlink code. Into the task, some of these should be pretty familiar to you. The only real different part is the implications. In the box to the right, declare our program version at the top. 0.6.7. Create the price consumers utility contract. Declare contract price consumer. Current version of the chainlink aggregator interface is v3. However, a chainlink adds more features to the interface. As chainlink adds more features to the interface, this version changes over time. When you name your contract, let's append this version in the name itself for data reference. And leave the body of the contract empty for now. It's probably gonna give you the same thing. So here there's a string. Do I have to make it equal? No, I always get them. Oh, probably the semicolon. Yeah, there we go. I always forget that. Now to have our contract pull the price from another contract, we need its interface API. Although where we currently are, we aren't sure what the interface of a chainlink data feed contract is. How do we get that? Importing the npm GitHub. Importing from npm GitHub. Did you know you can actually import code from outside your contracts? No, it's amazing. Oftentimes you don't have to have every piece of code directly in your project. You can borrow it from other applications. Once you import the aggregator v3 interface from the chainlink GitHub repository. This interface will include all the functions that we need to interact with a chainlink data feed contract, including functions like latest round data, which will return all the information we need. Here's what the full interface looks like. Interface aggregator v3. Just declaring functions. Get round data and last round should both raise no data present. You can find it in the GitHub repo for aggregator v3 interface. You can either import directly from GitHub or from npm packages to get this contract, or from npm packages. The framework you're using, like Truffle, Brownie, Remix, Hardhat, will determine whether or not to use GitHub or npm packages, but the syntax will be approximately the same. So I think I'm gonna write this down actually. I wrote down the definition for the functions to remember. So I'm gonna write it down here. Truffle, Brownie, Remix, Hardhat. I think Remix is an IDE. The other ones I'm not really sure what they do. Or frameworks. To work with the chainlink data feeds contracts, import the chainlink. So I think I'm just gonna copy this one. We've imported version 0.6 to match the version of Solidity we're using. So maybe if I do it, yes, no, it doesn't work. So what's up with this? I think I'm just gonna look. Oh, I forgot the import. Got that. I don't understand really well what this at does in the beginning. I think it's used for when you import something outside of the page. I've seen this in some places, and I think I tried to import something on a specific file in my computer, and it was throwing me an error because of this at here. Great work. Now to interact with one of data fed contracts. Since we already have the interface, all we need is the address. We can use the on-chain feeds registry, which is an on-chain contract that keeps track of where all these feeds are. Or we can just choose a contract's address of our choosing by browsing all the contract addresses. Reads from aggregator. The Chainlink feed registry is an on-chain mapping of assets to feeds. It enables you to query Chainlink data feeds from assets addresses directly, without needing to know the feed contract addresses. They enable smart contracts to get the latest price of an asset in a single call from a single contract. The feed registry only lists feeds with a canonical token address on a network. Non-token feeds, such as stock indexes, are not supported because they do not have a canonical token address. Feed registry fully supports the aggregator v3 interface API for multiple feeds. It maps feeds from base and code address pairs to get the latest link USD rounds from the registry. Chainlink data feeds contracts are updated on a regular basis by multiple Chainlink nodes. For implementation details, read Introduction to Data Feeds. Chainlink is a blockchain agnostic technology. This page lists the blockchain networks that Chainlink data feeds are currently live on, and details of where to access them. Another question I have is, to deploy smart contracts, is it the same on every protocol? What changes when you're deploying from one protocol to another, or how to bridge the gap between them? It's also confusing for me. Because I think I understand how tokens work. To swap tokens, you can swap in the same protocol, because the protocol are the rules for the network. But how would you translate something in one network to the other one if the rules are different? Maybe it's the same way that you connect front-end and back-end in the standard programming, where you have something that parses one contract to the other. And that contract is a smart contract itself. Probably people have thought about that already. I just don't know how it works. But it might be an interesting thing to look deeper on. I think we'll close this. Since we're trying to get the price of Ethereum in terms of USD, we need to pick the data feed that has this information. Important, each network will have a different address for each piece of data you want. The address of the Ethereum USD contract will be different on mainnet Ethereum from mainnet Polygon. Each network will have a different address for each piece of data you want. The address of the Ethereum USD contract will be different on mainnet Ethereum from mainnet Polygon, from RinkBuy, testnet, etc. We will use the data feed on RinkBuy for this demo. You can find all the addresses in the RinkBuy data feeds documentation. We are using RinkBuy because in later courses you'll learn how to deploy to the RinkBuy testnet. Put into the task. Create a public global variable available outside any function named price feed of type aggregator v3 interface. So I guess the type comes before v3 interface, public, price feed. Getter v3 interface, price feed. Create a constructor. Instantiate the aggregator v3 interface construct. Passing it mainnet Ethereum USD contract address as a parameter and store the result in the price feed variable. So price feed. I think maybe I have to do this, not price feed. I think because it's the constructor, but I'm not sure. And I'm not sure how to instantiate this. I guess they just call it like a function. To verify that you've specified the correct address of the Ethereum data feed contract deployed to the Linkbuy network, you should check the Ethereum data feeds page of the Chainlink documentation. Also here has all the contracts. Interesting. Just for Linkbuy Kovan and the mainnet. Okay. Oh, probably the other ones here. Yeah, this one seems very interesting to me. I think I'm gonna put this on my favorites to look at later. Instantiate the aggregator v3 interface contract. Also, I need to instantiate it here. So maybe I'll do this here, and then in the other one I just make it equal to this. Yeah, but then why would I make it equal here? So maybe price feed. I'm almost sure that this is incorrect. So let me take this. Yeah, it still doesn't work. So type aggregator v3 interface. Price feed. Create a constructor. Instantiate the aggregator contract. So maybe I have to erase this and instantiate the aggregator contract, passing it the mainnet Ethereum contract address as a parameter and store the results. So maybe I have to do this here, and then is an empty constructor. Still incorrect. Yeah, I'm not sure. I'm gonna look at the solution. Yeah, I don't know. So constructor should be public. And then I do have to put the stuff here inside. So maybe it was just the public that was wrong. But then why is it telling me to instantiate here? No, that's weird. I guess it's just a mistake there. The way they wrote. Because, yeah, I thought I had to do it outside because of the comment there. Now I must retrieve the latest Ethereum price by calling the latest round data function of the price feed contract. This function has all the information we're looking for, plus some. Round ID answer started at, updated at. Tuples, but before we do call this function, let me ask you something. Do you know what tuples are? If you recall the answer from our previous lessons, feel free to skip this section. Not just follow along and we'll explain. Tuple is a way in Solidity to create a synthetic grouping of expressions. The function returns multiple variables such as the latest round data function. You consider the return type to be a tuple of many types. In order for us to assign variables to each return variable, we use the tuple syntax by grouping a list of variables in parentheses. So it's destructuring the thing. We can also rename the variables to anything that we please. For example, let's rename answer to price. So just the order that matters. Additionally, if there are variables that we're not going to use, it's often best practice to leave them blank. This way we can easily see what variables are important to us and not declare anything extra. Create a public view function named function get latest price in public view. The returns and int. Call the latest round data function of the price feed contract. The latest round of this function. Store only the answer in an int. So be int, then this answer. Then 3. So 1, 2, 3. Call the latest round data function of the price feed contract and store only the answer in an int variable named price. And now, so it has to be price here instead of answer, I think. Exclude any other variables from being declared in our function call. If you can't remember the syntax for doing this, check the example from above. But first, try to do it without picking. Return the price variable. Yeah, so I have to pass multiple arguments here. And maybe I have to put price feed dot latest round data. Exclude any other variables from being declared in our function call. But what do I need to pass here? It doesn't say that it needs any arguments here. So maybe price feed comes inside of the arguments instead. But then how does it know that I have this function here? That's just because of the constructor. It's gonna inherit all the functions from the interface. So let me try it this way and see. Okay, so this part now is correct and this is not. Also, I have to put the int inside of the thing. So int price. And I'm probably doing one more than necessary. Yeah. We now have a function that can pull the latest price of Ethereum in terms of the United States dollar. Now, as you know, this decimal spaces don't work so well in Solidity. So what happens when you try to call this function? Can you guess how the answer is going to look like? Well, to save your time, if we were to call this function, we'd get a response similar to this. Is Ethereum really that expensive? Well, maybe sometime in the distant future it might be. But at the time of writing, it's not even close. Right now, the price is about 3,000. So how do we know where the decimal place goes? This is simple. There is a decimals function that tells us. Can you make a get decimals function that returns how many decimals this contract has by just looking at the interface? So get decimals. So it's probably gonna be by dividing, getting the remainder somehow. How many decimals this contract has by just looking at the interface. Or activating this decimals thing, decimals function. Call that get decimals public view. It returns the result of the decimals function. So I need to specify return maybe. Returns probably it's an int. Uint 8. So I need to return price feeds, not decimals. The first line of code, function and store the result in a variable named. So I'm not sure if I should destructure this, probably not. Uint 8 decimals. And then I return decimals. I think I'm gonna go to the bathroom real quick. You now know how to get data from the decentralized Oracle network into your smart contracts. Once you finish once you finish this lesson, you can follow along in the Chainlink documentation basics tutorial to learn how to deploy one of these to real testnets. Yeah, the thing is, I don't know if I can do this thing on stream because I don't want to show my wallet. That's the problem. You'll learn later how these price feeds work under the hood and how you can set up a DOM to gather any data that you're looking for. However, often developers choose to work with some of these out-of-the-box Oracle services since they are much easier and require almost no time to set up. We'll keep learning more of these ready-to-go out-of-the-box services. There's so much more to Chainlink oracles than what we've just covered here, and we're going to go over how this all works, as well as some other incredibly powerful features. However, we want to give you a heads up on some tools that bring your developing to the next level. Soon you'll learn how to work with Truffle, Hardhat, frontends, DeFi, and more that bring Chainlink data feeds to life even more. Once you learn some of those concepts, you can come back to the Truffle starter kit, Hardhat starter kit, and Brownie starter kit. To build sophisticated smart contract applications in development suits. Let's see what languages. JavaScript and Solidity. So I guess most of the work is done on JavaScript. Just save gas. And then, usually from what I've seen, that's how people do it. Either JavaScript or TypeScript is the most common I've seen so far. And Solidity. We're just gonna add to the favorites. But until we come to those, let's keep learning about some of the amazing features Chainlink has to offer us. Select the next button to move on to the next chapter. Also, I guess this doesn't have a challenge. Pseudo random DNA. At this point in our contract, we have been working with pseudo randomness. Our CAC 256 function was a great way to get started learning about how to create smart contracts. However, as we mentioned earlier, you can run into some major issues when creating smart contracts that rely on pseudo-randomness. Everything that is part of the on-chain mechanism is deterministic by design, including our hashing function. When we tried to get random DNA from a string, we know that the DNA we are going to get is going to be the same every single time. This means that our randomness creation function isn't actually random. We also can't rely on someone being honest when they input a string into this function. So how can we fix? Well, a naive approach is to use globally available variables like message.sender, block. So now we should be clear that everything inside the blockchain is deterministic and can lead to exploits if you try to use randomness from inside the blockchain. So how can we get randomness from outside the blockchain? Guessed it, with a Chainlink oracle. Let's take a look back at our good friend the zombie code where we give the pseudo random DNA and let's try to fix it. This time though, we will use the secure randomness of the Chainlink variable randomness function. So guys, it creates the random function in JavaScript and then passes through the blockchain with this send thing. I'll look into this stuff later probably. Is a way to get randomness from outside the blockchain, but in a proven cryptographic manner. This is important because we always want our logic to be truly incorruptible. Our naive attempt at getting randomness outside of the blockchain would be to use an off-chain API call to a service that returns a random number. But if that services goes down, is bribed, hacked, or otherwise, you could potentially be getting back a corrupt random number. Chainlink VRF includes on-chain verification contracts that cryptographically prove that the random number the contract is getting is really random. Yeah, that brings me another question, which is, what is truly random anyway? Is it possible for something to be truly random? It's another whole debate. What even is randomness? And why do you have the distinction? Of course, the distinction is based on patterns, but yeah, it's a self-fulfilling prophecy at the end of the day. Now, this is where we will be introduced to the basic request model of working with oracles. The first step is when a smart contract called the Kali contract makes a request to a Chainlink node, which is comprised of a smart contract and the corresponding off-chain node. When it receives the request, the smart contract emits a specific event that the corresponding Chainlink node is subscribed to looking for. This happens in one transaction. The Chainlink oracle will then process the request, be it randomness, the data request, etc., turn the data computation back to the Kali contract. Our contract will in turn send the response to the Kali contract. This middle contract is often referred to as the oracle contract. This return process happens in a second separate transaction. So in total, the basic request model is a true transaction event. Therefore, we take at the very minimum 2 blocks to complete. This true transaction architecture is important because it means that brute force attacks on randomness or data requests are throttled and impossible to hack without costing the attacker insane fees in gas costs. To recap, the process is as such: Kali contract makes a request in a transaction, Kali contract or Oracle contract emits an event. Chainlink node off-chain is listening for the event, where the detail of the requests are logged in the event. In a second transaction created by Chainlink node, it returns the data on-chain by calling a function described by the Kali contract. In the case of the Chainlink VRF, a randomness proof is done to ensure that the number is truly random. Now, similar to when we make a transaction on Ethereum or any Solidity compatible blockchain, as you know, we have to pay some transaction gas. To work with oracles, we have to pay a little bit of oracle gas, also known as the link or Chainlink token. The link token is specifically designed to work with oracles and ensure the security of the Chainlink oracle networks. Whenever we make a request following the basic request model, our contracts must be funded with a set amount of link, as defined by the specific oracle service that we are using. Each service has different oracle gas fee. Why didn't we do this with the data feeds? Now the question then becomes, why wasn't this done with data feeds? Or why didn't we pay oracle gas for the data feeds? These are really good questions. With data feeds, an entire group of Chainlink nodes are being requested for data instead of just one Chainlink node. Hence, it's a decentralized oracle network. However, only one entity has to kick off the request to the whole network. So we were able to benefit because someone else already created the requests to the oracles for the different kinds of data described in the data feeds. Data feeds are sponsored by a group of projects all making use of data feeds such as Aave, Compound, Syntax, and more. And the updates to the network are being kicked off programmatically whenever there is a slight price change in the data they are reporting. Working together as a group, we can keep transactions costs down and create this collective good the whole ecosystem can benefit from. In summary, someone else followed a bit more advanced version of the basic request model for us with the data feeds. Chainlink, yeah, but that's another question. Can they manipulate this? Because they are the ones that are making the requests. I guess not if there's a bunch of them, different ones, but it's possible. The Chainlink VRF follows the basic request model with one added benefit. Since there is a cryptographic proof on-chain of the randomness of the number from a Chainlink VRF node, we are safe to work with a single Chainlink VRF node. As the technology gets better and better though, even more decentralized versions of the Chainlink VRF are being created, but luckily we are good to work with this secure method of randomness for our smart contracts. We aren't going to go deep into the proofs the many researchers have done to ensure the randomness returned by Chainlink VRF nodes, but here is basically what's happening for this magic to occur. In brief, a smart contract requests randomness by specifying a hash used to uniquely identify Chainlink oracle. The hash is used by the Chainlink node with its own secret key to generate a random number, which is then returned to the contract on-chain along with a cryptographic proof. As on-chain contract called the VRF coordinator takes the random number along with the proof and is verified using the oracle's public key. Relying on the widely accepted signature and proof verification capabilities of blockchain, this enables contracts to consume only randomness that has also been verified by the same on-chain environment running the contract itself. You can check out the Chainlink VRF contracts to see the exact functions the system is using. There's a lot of big brain concepts here. Let's finally dive into learning how to pull a random number into our smart contract. Get started by once again pulling the Chainlink VRF contract node from npm GitHub that allows us to interact with a Chainlink VRF node. We are going to inherit the functionality of the VRF consumer-based contract code into our code to emit events and define what functions the Chainlink node is going to respond to. Import the VRF consumer-based.sol Solidity version 0.66. That's pretty much this. The VRF consumer-based.sol includes all the functions we need to interact with Chainlink VRF coordinator and node. So again, the missing imports should be lowercase. You got it. The VRF consumer-based contract includes all the code we need, send requests. Regardless of Chainlink token contract, this needs contract. You find out these variables in Chainlink. Once again, the addresses, blah blah. Use a constructor of an inherit contract to just put the constructor declaration as part of a contract constructor. Have our zombie factory contract inherit from VRF consumer based contract. If you don't remember the syntax, here's an example. Create a constructor for the zombie factory contract that calls the constructor of the VRF consumer base contract. So it's this one. Constructor. Passing with addresses of the VRF coordinator and link token contract from the Rinkby network as arguments. So I guess this here. Oh, I need to put the name as well. I forgot. I didn't know actually. that you need to specify the name for the constructor. I guess it makes sense, yeah, based on other programming languages where you have the init in Python. I think JavaScript is constructor as well. But I think on the previous lesson I didn't put a name and it worked. So it's kind of weird. Oh, and it is also like this. Still something wrong. Oh, public. Also, here are the arguments for the constructor, and then here it goes, the logic, I think. It's still wrong. And if I raise this, it's probably the issue. So, or maybe I actually don't need to put this here. Oh, actually. No, I think I'm gonna look at the solution. Calls the constructor of the VRF consumer base contract. Also, the constructor is calling the other constructor. That's why I have the name, I think. But it's still wrong like this. Maybe it's the same column. Yeah, I don't get it. Just checking to see if I have any typing mistakes. Oh, so I have to create it here. Maybe. Let's go back to the beginning. Yeah, so it's probably here. No. Yeah, I don't know. I'm gonna look at it. Oh, this is the problem. Probably typed as a mistake then. This should be like this. Now it's probably correct. Yeah. Binary chain link VRF variables. Now this part is pretty easy. We just need to define our key hash and fee in our constructor. We also should make a global variable called random result that will store the most recent return of the chain link VRF. Find the key hash. So bytes per issue over key hash. 6 public. Fill in the body of the newly created constructor by setting the key hash variable true. So key hash to this. That should be a string probably. And the feature this number. Oh, actually, I'm not sure if it's a string. Because bytes 32. It probably is a string, I think. So maybe not. Yeah, there we go. So it is in a string. I don't really understand the bytes 32 thing. Guys, it's just 32 bytes. Whatever. I'll look at this later probably. Request randomness and fulfill randomness function. Now we can create our function that calls the chainlink node. Remember, the chainlink VRF follows the basic request model, so we need to define a function to request a random number, a function for the chainlink node to return the random number true. Remember, the chainlink node is actually going to call the VRF coordinator first to verify the number is random. Then the VRF coordinator will be the one to call our zombie factory contract. Since we are importing the VRF consumer base contract, we can use the two built-in functions that do both of this. A request randomness. This function checks to see that our contract has link tokens to pay a chainlink node. Then it sends some link tokens to the chainlink node. Emits an event that the chainlink node is looking for, assigns a request ID to our request for a random number on chain. Fulfill randomness. The chainlink node first calls a function on the VRF coordinator and includes a random number. The VRF coordinator checks to see if the number is random, then it returns the random number the chainlink node created, along with the original request ID from our request. So let's create these two functions in our contract. We need to the task. Create a function named getRandomNumber. It is a public function that returns a variable named request ID of type bytes 32. Function getRandomNumber. A function that returns bytes 32. I don't think I need, maybe I need to specify request ID. The body of the function returns the value you get from calling the request randomness function. So request randomness should be from the VRF consumer base. Maybe I don't need to specify anything because it's on the constructor, but I have a feeling that's not gonna be correct. Because they probably need to specify something. Passing into parameters key hash and fee. Parameters key hash and fee. So that's probably, yeah. And that makes more sense. But I'm still not sure. Let's do it in one line of code to keep things clean. For more details, see the get random number page of training. Create an internal override function named fulfill random. internal override. Bytes 32, request ID, joint 56. This function assigns the response of the chain link, the randomness argument, node to the random result variable. So random result equals the response of chain link randomness argument. Why requested? Maybe I should put request ID inside. Why did we make this function internal override? It's because only the VRF coordinator contract calls this function. So I'm not sure I'm doing things correctly. So there's also a problem. Maybe I don't need to specify request ID. So request ID bytes 32 returns the value you get from calling the request randomness. Passenger arguments. Create an internal override function named for pure randomness. Request ID bytes 32. Randomness true 56. This function assigns the response of the chain link the randomness argument. So maybe I should be calling get random number. It takes two arguments, request ID and randomness. Function sign the response to chain link randomness argument. Node to the random result. Also fulfill is on the name, the mistake. And then here, I'm not sure. Oh, so it works, okay. Just that mistake. We've done it. Your contract now can get a random number. Now let's delete all the pseudo-random number generator we're using through randomness now. Delete the old pseudo-random generator. So this one. When you finish the lesson, you can learn more about chain link and random numbers by following the random numbers tutorial. Yeah, I guess it's pretty much the same. Same thing here. I forgot to check for the answer. All done, we've completed the lessons. Okay, now I think I'm gonna take a break, and then I'm probably gonna come back later on today and try to finish this. It's probably not gonna be possible to finish everything one day, but yeah, I'm gonna try. So see you then.